Hi, my name is Per Nyberg. I'm from Quantum Machines, where I lead our strategic markets and alliances. And today I'd like to talk a little bit about the heterogeneous endgame of quantum computing. So first of all, a little bit of definition. So what exactly is heterogeneous? This is certainly a term that's quite commonly used in a number of the computing industries. In quantum, you hear often the word hybrid as well, and they're certainly related, but fundamentally, this is all about computer architectures, computer systems, infrastructure that is composed of similar or diverse ingredients or constituents. So you can think of systems that are composed of both GPUs and x86s. And really the point here is that there's very few systems today where they are homogeneous in nature and is really all about taking advantage of different types of technologies for different purposes. So a little bit about kind of what we're seeing in the market today as a situation assessment. So first of all, hopefully all of you would agree that the potential of quantum computing is established, right? I think that groups around the world are really looking at quantum computing not from an if perspective, but a how. And this is important because it means that it's not that there's no more further research to be done, but really, we're transitioning out of that phase of, just basic assessment and really starting to look at, practical implementations of quantum computing in end user verticals or domains or applications. But that also means that we're now starting to reach some very important inflection points. As I said, a lot of if you look at the quantum industry today, a lot of it has been in the research lab. Right, work done by pioneering scientists and engineers around, demonstrating, the viability of the technology. And what's exciting is that we're now starting to look at usable scale. So, what sort of scale do you need in terms of qubit count, for example, to really start to understand the potential of quantum processors, but obviously looking into the future about where you start looking at quantum advantage. And along with that comes, a whole host of commercialization questions. So one of them, for example, is, as I write there, about, homegrown to commercial grade. And, we're really moving towards, robust, purpose engineered technologies. As I said, today, many things are in the lab. And when you start to, from a company perspective, start looking at shipping, product at scale, for example, or even just building systems at scale, there's a whole host of requirements that really come into play. And so this is a very exciting area and really one that demonstrates, again, not only the viability, but really the importance of looking at engineered solutions. The second one is around scale. And so what happens with scale is very interesting. There's both technological questions, let's say, as you scale up in qubit counts, error correction protocols, performance characteristics. But there's also commercial considerations as well. Just things like, for example, the, power and cooling and the bill of materials, if you will, as system sizes grow, they start to become very important factors when people consider scaling up. And the third one is around this notion of practical quantum computing. And this is really, really exciting and obviously a critical point as well. And really where, the market starts to become, the demand is being pulled from the users. And really what they're starting to explore now is, what's that end game, right? So once quantum computers become, you reach, let's say, quantum advantage, for example, or even before that, how exactly is quantum computing going to be adopted within applications? So if you are let's say, a financial services institution, or you are a pharmaceutical company looking at drug discovery, how will quantum be used? It's unlikely that, all applications will be pure quantum. You will have, as I mentioned at the beginning of the presentation, on this notion of heterogeneity. And so the question is, and these CIOs that might be looking at this is how do I adopt quantum technologies into my existing infrastructures? So if you look at the high performance computing community, if you're not familiar with them, this is kind of the, they're called also the kind of the supercomputing community. And, kind of by definition, this community has, quote unquote, the sort of fastest computers available at any given point in time. Obviously, high performance computers or supercomputers from 20 years ago are sort of desktop almost today. But really, there's been a lot of lessons from that industry in how to adopt new technology, because they are typically at the forefront of advanced technology adoption. And I think there's a couple of key lessons that we can learn from as we look at, what is, how will quantum be adopted? How should we be thinking about the engineering or design of quantum systems or technologies such that we facilitate adoption? So first of all, when you think about, really quite fundamentally what it is that why new technologies are adopted, it's really quite simply the need for greater capability. You want to run a higher resolution model, for example. You want to run faster. This is really, and it sounds obvious, but this is what drives new technology exploration and adoption. So when you look at a couple of examples, these are from obviously the automotive industry, and back in the 90s when car crash simulation first became kind of state of the art, and quite frankly was even regulated that this was something that was necessary for car manufacturers. What drove this was, they needed to run higher, resolution or mesh sizes for car crash simulation, and they need to constantly look at faster and faster capabilities to get greater fidelity in their models. Another example was looking at all the way, not only, kind of, parts of the car, say the front, left side, let's say, of the car being crashed into some object. They even got this down into looking at sort of real-time human body modeling as well, with the advent of GPUs, which provided the performance for them to be able to do this. But these new technologies also drive the creation of new methods. So, once you give, sort of this new capability in the hands of engineers, they will design entirely new ways of approaching problems. And this is really one of the really exciting things that these new technologies drive. So it's not just doing current things faster, it's doing entirely new things. And so one example here is with the advent of machine learning. Engineers were able to look at sort of automated analysis of simulations. If you're running, let's say an order of 1,000 simulations, it very quickly starts to, reach beyond the capability of, just a couple of engineers looking at this quite manually, to be frank. And the automated approach that machine learning provided, created an entire new method or improvement to the process. And so you end up with this very kind of a symbiotic relationship between, again, this need for greater capability, adopting new technologies, and then also these new technologies creating new methods. And, you end up, like I said, this sort of virtuous circle of advancement. So this is kind of the first lesson around adoption. The second lesson is really around integration. So once you've proven out these new technologies, what really is that kind of path that they take? So one thing first to recognize is that, these new technologies actually typically just accelerate algorithms. It's rarely entirely new, the entire applications. And so, one example is, again, using one from the AI space is looking at vehicle vibration shapes using deep learning, right? So this is just one part of a model, right? And so you can look at these models as, they have larger applications or as a workflow. So again, continuing on the theme of the automotive industry, things like, automobile NVH, noise, vibration, and harshness simulation. Now, all of a sudden, you have, deep learning as one part of a larger workflow. And then, of course, these workflows over time become increasingly, heterogeneous. You're starting to use different technology. You're using multiple disciplines as well. Again, sort of, classical simulation along with machine learning. And those are then, they have particular characteristics from a performance perspective. And then you start to build this, this growing heterogeneity from a technology perspective. So if you look at modern applications, they are incredibly complex and really make use of a number of different approaches and a number of different technologies. But the lesson really here is that for new technologies to be adopted, they must be integrated into the workflows. If you can't do that effective integration, it really kind of halts their adoption. So this is really fundamentally where both that kind of adoption and integration come into play. And this is really the lesson for quantum computing. So I'll use kind of another example as well. Sort of the third kind of highlight out of HPC is that what you also see is this cadence between new technology adoption and integration. So I'll use an example from the weather and climate space, in particular, kind of numerical weather prediction. So the first example is, starting with NWP, numerical weather prediction, or climate prediction. This has, the first NWP models were run in the 1950s, in fact. But really, since the 1970s, they were using kind of, the latest computing, supercomputing in particular. And if you look at where they've evolved to today, they've, again, very heterogeneous. They use both, kind of x86 and GPUs, and they've gone from single processor to massively distributed. If you look at the large weather centers today, they'll be running across, potentially thousands of processors, or potentially hundreds of thousands of cores to run a single model. And then a few years ago, machine and deep learning became, a viable technology. But if you look at the early sort of adoption of this new technology, it was really characterized by standalone applications. So they tend to prove this out in a standalone application. It could be using, in this example that I show here, feature detection, same sort of feature detection you would use in automated vehicles, but applying it to historical data sets to try and be able to identify the features, let's say, of storm detection in again, historical data sets, right? But it's a standalone application. Then they moved on to what's kind of called, cognitive simulation. And here it's really about embedding this new technology, integrating that new technology, as I spoke about on the previous slide, into these larger models. And now you can go from, just kind of, again, standalone applications, characterizing something on, let's say, historical data sets, to really potentially real-time prediction of complex phenomena. But again, the important message here is that you've now integrated this new technology. And if you look at quantum simulation, that'll probably happen, again, on standalone models. In the weather space, that could be perhaps looking at, atmospheric molecular clusters. And then as time goes on, once that's been proven out, you will look into integrating this quantum capability or quantum acceleration into the larger models. And now you have what I'm terming here, a complex quantum cognitive simulation. And again, you see the point here is that you're now able to embed a number of different technologies to essentially achieve a simulation or scientific capability by being able to take advantage of different methods, different disciplines, and ultimately different technologies, but all integrated into one model, so you can really explore very detailed areas across, physical and chemical and biological processes at a range of spatiotemporal scales. So as I've pointed out, all of these industries, and I showed a couple of examples in weather and automotive, have really benefited from heterogeneous infrastructures. This has been, state of the art in high performance computing for a number of years. And, again, as I hopefully have demonstrated, for very good reason. you really are able with these novel technologies to perform simulations that you couldn't otherwise do, right? And so really what we're looking at now from a quantum perspective is that, we need to deliver the solutions that will be able to be adopted and integrated into these various industries so they can truly take advantage of the potential of quantum computing. So if you look at the quantum technology stack and the general computing stack, really what you're now talking about is, merging these two into one large stack. For the most part today, if you look at, the quantum computing industry, we tend to focus mostly on that quantum stack. In a lot of ways that starts at the control layer and then down to the quantum processors. The general computing stack will obviously extend much above that into workflows, hybrid applications, and they come with their own set of software layers as well around, just general system management, operation, job flow, and then programming. So really what we need to do, the challenge here is to effectively integrate both of these and really to make it, usable and such that it's delivering the performance to be adopted within the general stack. We're going to need a very tight coupling between the quantum stack and the general computing stack. And really where much of this happens is at that quantum control layer. That's really the first point where the, call it classical computing stack or general stack, touches the quantum world. And so one of the really important things here is that quantum processors and quantum computing and quantum technologies do have a very unique set of requirements. This is a very, very different technology compared to classical technologies. And so one of the important factors here is to efficiently expose these unique requirements up into the higher levels of the stack. So just think of calibration, for example, as one, all the way through to hybrid algorithms and even QPU abstraction. There is absolutely interest in being able to run different types of quantum processors within a single system. So again, this effective integration that's a critical step for, again, the adoption and ultimately the success of quantum computing. So let me tell you a little bit about quantum machines. So really what we focus on is the ability to bring the best out of any QPU and really focusing on achieving the fastest time to results. This is very much, has been, the essence of the technology that we've built from the very start. And, we believe that this is two of the, most important factors in really bringing about this adoption of quantum computing. So a little bit about us. We are the largest quantum control company in the industry. We are very proud of our quantum passionate experts that we have around the world. We're also one of the largest funded companies as well in the quantum space. And much of our emphasis or focus has been in, real-time control, hybrid quantum classical capabilities, and multi-QPU support. And we've really been pioneers in these areas. And this is something we're very, very proud of. We've got a large customer base around the world across, large enterprise, startups, national labs, and academic institutions. And so if you look at the stack, what you see here is a schematic of the quantum control stack that we deliver. So starting from the top, this is about exposing the pulse level capabilities through the QA programming language. We support OpenQASM 3. So this is really the tie-in into the higher application levels. And then through the pulse processor, through the analog front end, and then all the way through to the QPUs. And so I'll kind of highlight a few of the different technologies that we feature. So one of them is the pulse processor. This is very much the heart of our technology stack. This is what supports or provides the real-time capabilities, and in particular, the real-time hybrid quantum capabilities. And really what this this performance advantage allows you to do is really run the most complex algorithms and experiments in record time, and it also scales as well. The second is QA, which is our pulse level quantum programming language. So this is a Python-like language that's very intuitive and comprehensive. And what it allows you to do is really expose the lowest level capabilities, but in a very programmable way. So a lot of what we hear back from our customers around, productivity and the ability to, not only run experiments quickly, but also develop experiments quickly and iterate very quickly as well. And this is employed by, hundreds of physicists and engineers around the world on our systems. And it also supports across all the major gate-based QPU architectures as well. And then finally, the analog front end. This is obviously the technology that connects into the quantum processor, massively scalable, and again is QPU agnostic and supports all the major gate-based architectures that are in the industry. And again, we've got customers across all of these various areas. So, just as sort of a summary of the quantum orchestration platform, we really believe that this is, the kind of foundation for not only scalable quantum computing, but ultimately for practical quantum computing as well. And so, I've talked about some of the capabilities for scale and real-time capabilities to run, the most complex algorithms to enable the advancement of quantum error correction. These are obviously critical things for the industry to mature and grow such that we can reach, the milestones of quantum advantage and just overall system robustness. And I've talked about the ability to program very low level pulse level capabilities, but in an intuitive, comprehensive way, and the support for multiple architectures. And if you sum all of this up, really we feel that this is also the foundation layer for effective high performance computing and quantum computing integration. As I mentioned on an earlier slide, the control layer really is that first point of contact into the quantum world, and the point at which we will be looking at integrating into larger classical infrastructure. So some takeaways, embracing quantum's role within the heterogeneous environment is really key to its ongoing development. I hope I showed that, this is some lessons from the high performance computing community that really demonstrate or highlight the importance of this adoption and integration, and ultimately the heterogeneity of workflows and the infrastructure. But achieving this and effective integration, it will have vast implications on the quantum stack, right? And this is really, really important, I think, for us as an industry. And this is something that we at Quantum Machines are striving for, is to build in that effective integration. And from our perspective, we're going to continue to pioneer those areas around, like I said, real-time control and just overall optimal control of quantum computers, and to build this foundation for the realization of practical quantum computing. And with that, I thank you for your time.